Hello. In this video tutorial, we're going to take a look at AP Physics 1 Dynamics homework, Newton's third law. Remember to pause or rewind the video as needed. Number 1. A student performs an experiment using two carts 1 and 2 on a straight track. Both carts can roll without friction and are equipped with springs. The student sends cart 1 to the right toward cart 2, which is initially at rest. A student uses motion detectors to measure the positions of both carts as a function of time. The cart springs collide between the t2 seconds and t3 seconds. The graphs of the student's data are shown where right is considered to be positive. Part A. Fill out the action-reaction, cause and effect table below for the interactions between the two carts. Since the carts are equipped with springs, the type of force they exert on each other is called elastic force. Make sure your cause explains the agent, object, type of force, direction, and whether it is a push or pull. Well, we can begin. Let me zoom in on this. We can begin by saying that cart 1 pushes cart 2 to the right, so with an elastic force. So cart 1 applies an elastic force on cart 2 to the right. The reaction is basically the opposite thing from the other object, meaning cart 2 simultaneously pushes cart 1 back to the left, also using an elastic force. The effect of this in terms of the action, so if cart 1 pushes cart 2, the effect is that cart 2 speeds up going forward or going to the right. Cart 2 speeds up to the right. After cart 1 applies the elastic force. Now in the reaction, cart 2 pushing back on cart 1, well, that means cart 1 will reverse direction, rebound if you will. Cart 1 reverses direction after the collision between the two carts. Part B. Which cart has the greater mass? What evidence from the graphs support your assertions? Hint, it has to do with the change in motion. Less change in motion, meaning acceleration, means greater mass. All right, acceleration and mass are inversely related to each other. So bigger objects have less acceleration, less change in motion. Well, cart 2 had less change in motion, and we can see that in the graph. Take a look at the graph. The cart 1 does this. It has constant velocity motion for 2 seconds, collides with cart 3, and then rebounds backward with constant velocity, and that's a whole lot of change in motion. Cart 2, on the other hand, is at rest for 2 seconds, and after the car hits, then moves forward. So cart 2, having less change in motion, less acceleration, has more mass. Part C. Using the graphs from above, calculate the acceleration of each cart. Well, remember, acceleration is the change in velocity over time. And velocity is the slope of position time graphs. So we're going to have to use the velocity to get the slope to get the velocities, and we can use this equation to calculate the accelerations. Let's go up and find those slopes. So this first one here, slope of segment 1, and then the slope of segment 2 over here after the acceleration. So the first one looks like we're going up 1 and over 2 seconds, so that's a slope of positive 0.5. And then here we're going from midway here to midway here, and it looks like we go down 1, 2, so down 2 over 2, down 2 over, let me see, look at that one more time. Down a half, excuse me, not down 2. Okay, so we have a slope of negative 0.2 meters per second. Again, there's the acceleration right there. You can tell because of the curve. Here, velocity is 0. And for this segment here, we're going up from here to here. So that's 4 boxes. 4 boxes on this would be 0.4. So we're going up 0.4 over 2, and so it's the same 0.2 slope, but positive. So instead of negative 0.2, it's positive 0.2. Okay, so we've got our velocities to work with. Okay, and again, the acceleration takes place from 2 to 3 seconds. That's a 1 second time interval. And so here we go. The acceleration of cart 1, right, is v minus v naught over t, where cart 1 has a final velocity of negative 0.2 and an initial velocity of 0.5. This occurs over 1 second, and therefore the acceleration of cart 1 is negative 0.7 meters per second squared. In other words, there's a lot of change of motion going on there. The acceleration of cart 2, same idea. velocity v minus v naught over t. This one is going to be 0.2 minus 0 over 1. Part D. If cart 1 had a mass of 0.2, what is the mass of cart 1 has a mass of 0.2? What is the mass of cart 2? Explain how you use Newton's second law, Newton's third law, and your answers from part C to make this determination. Well, using Newton's second law, we know that the net force on cart 1 equals mass of 1 times acceleration of 1. So we can go 0.2 kilograms, that's the mass of cart 1, times the acceleration, which was negative 0.7, and we get negative 0.14 newtons. Now, using Newton's third law, the net force on 1 is equal and opposite to the net force on 2 when they collide. Therefore, the net force on 2 would be positive 0.14, because you're going the other direction. And the acceleration could be found by going net force divided by mass. Back that up. Mass could be found by going net force divided by acceleration. The net force being 0.14 newtons divided by the acceleration of cart 2, which we found on the graph to be 0.2 after the collision. Dividing those, we can see that cart 2 would be about 0.7 kilograms. Number 3. A student of mass m as a part of an athletic competition is connected to a box also of mass m by a rope tied around his waist. Initially, the student is at rest on a rough surface and the box is at rest on a frictionless surface. At time equals 0, the student begins to run to the right, but the rope is slack enough so that the box does not begin to accelerate. At time equals 2 seconds, the rope suddenly becomes taut and the box jerks into motion along the frictionless surface. At t equals 4 seconds, the box crosses from the frictionless surface onto the rough surface. The student accelerates due to the force of friction of magnitude F between his shoes and the rough surface. The box, upon crossing onto the rough surface, experiences a frictional force of 1/4 this friction. Let's diagram out what's going on here. This region here, that is the frictionless region. That is the rough region with friction. So you can see the runner from time equals 0 to 2 seconds, you just have the runner accelerating. Okay, so here, from here to here, only the runner accelerates. And then from 2 to 4 seconds, this range right here, you then have you have a system. You have the runner, box, system, but the box is not encountering friction. Then from here to here, you have runner, box with box on rough surface. So So runner box system, right, with friction on the box. Okay, so just sort of highlighting what's going on in the problem. Part A, draw a free body diagram for the student, a free body diagram for the box, and a free body diagram for the student box system at the times indicated. So at 3 seconds, that would be right here when it's the student, when it's the runner box system. Okay, and so what's going on there is you have the force on the box. Now keep in mind, the box and the student are both mass M, so they should have the same weight. So let's go ahead and draw that. I'm just going to draw a couple arrows going down, a couple spaces going down. There would be the weight of the box and the normal force of the box. Now there's going to be a force due to tension going to the right because the box is being pulled to the right. Since the box is still on the smooth surface, there is no friction at this point. Now the force on the student, however, you've got the same tension force pointing in the opposite direction, this time acting on the student. You've got a force of friction just a little longer than the tension because the system is accelerating. And you have the same weight, same weight and normal force as you do the box because the, so this is the weight of the student and the normal force of the student. So actually, to draw this proportionally, here's how we need to fix it. One, if normal force is drawn 2 units long, friction should be shorter. So I'll make it like, 1.5 units long. And tension should be shorter than that because you're accelerating to the right. That means this tension here would be 1 unit to the right. Okay, and that kind of fixes everything. Now, the external forces would simply be friction because tension's an internal force. So we've got friction going to the right, and you've got the normal force of the box student system. Just like you have the combined weight of the box student system. So it's probably better to do in this case. We'll do it a little bit differently than we did it in the last example. We'll go ahead and draw 2 separate arrows. So normal force for the box, normal force for the student. Similarly, we'll have weight of the box and weight of the student. Okay, now at 5 seconds, what's happening is the box is now on the rough surface. Okay, so all things being equal, the weights are exactly the same. Number 2, a horse connected to a cart by a rope pulls the cart forward on a flat road. Assume the friction, the force that allows the horse to accelerate forward, but that the cart itself experiences no friction. Part A, fill out the action-reaction cause and effect table below for the interaction between the horse and the cart. Be sure your cause explains the agent, object, type of force, direction, and whether it is a push or pull. Well, the horse pulls the cart forward. The cart reacts and pulls the horse backward. Now the effect of this, the effect of the horse pulling the cart forward is that the cart is accelerated forward. The result of the cart pulling the horse backward is that the horse is held back by the cart. Part B. Draw a free body diagram for the cart, a free body diagram for the horse, and a free body diagram for the cart-horse system. Assume the horse has a greater mass than the cart, and the horse pulls the cart to the right. Okay, so let's focus on the cart first. So we've got weight going down. So weight of the cart going down, and then you've got normal force going up. They should be balanced. And you need some tension force pulling the cart to the right in the direction of its acceleration. Now on the horse itself is going to have a much larger weight. So I'm going to put a few units. I'm going to make it a little longer. So we have the weight of the horse balanced by the normal force acting on the horse. You have a tension. The tension that pulls on the cart pulls on the horse by the same amount. That's why it's the same length, but pointing in opposite directions. And then lastly, there needs to be a friction force longer than this to get the cart accelerating. So I'm going to draw a friction force at least 4 units long pointing to the right. And the friction is what's acting on the horse's feet to get the motion going forward. Now the forces on the system would be basically combining all of it. So I could combine the normal force and just say normal force 5 units long of the normal force of the horse cart system, right? And then you've got the combined weight of the horse cart system. Or you could draw separate arrows for each one. Either one works. And then for the system, all we have, since these two kind of point opposite directions, the only thing we have left for the system is the force of the friction moving forward. Part C. A student claims that the 2 forces you listed in Part A cancel out so that the horse and cart cannot move. In a brief paragraph, correct the statement and explain to the student how the horse and the cart actually move and what the forces you listed above actually do. Okay, so the tension well, they do not necessarily cancel. Because they are on different objects. The horse moves because friction to the right from the ground exceeds the pull of tension. On the horse to the left. Thus, the horse accelerates forward. Since the horse accelerates, the cart accelerates. The cart moves because tension pointing to the right is unbalanced on the cart. So let's begin by drawing the weight and the normal force on the box and student. So it's going to be exactly the same. Weight of the box, weight of the student. Normal force of the student, normal force of the box. Okay, now again, this time the force of friction on the student kind of has to be very similar, okay, to what happened before, because the force of friction on the student is due to the student's weight, normal force, and the coefficient of friction between the roughness of the surface, ground, and their shoes. So the friction force isn't really going to change from the previous problem either. Okay, but here is what's going to change. So we've got the tension going the other way. Tension is about 1 unit pointing that way. And then we've got the same tension pulling on the box to the right, but you're going to have friction and a really small amount of it going that way. And again, friction has to be less than tension because the box is accelerating to the right. Okay. And so what does the external forces look like? It's going to look like the same as this diagram here above. The difference is you now have friction. Well, so the friction on the student, right? And then you've got friction on the box. Just sort of differentiate right there. Let A1, A2, and A3 be the accelerations of the students at 1, 3, and 5 seconds respectively. Rank them from greatest to least. Put an equal sign between any that are equal. Well, the accelerations are going to be the greatest. So acceleration is greatest when net force is greatest. And if we look back at the situations again, at 1 second, now 1 second is just the student running, hadn't pulled the box yet. At 3 seconds, that's when the box is being pulled, right here, from 2 to 4 seconds. 3 seconds would be in that time interval. And then finally, 5 seconds is after the box is on the rough surface. So what we basically have here is this is the largest net force. Largest net force. This net force is a little smaller. And then this net force is the smallest. Meaning acceleration in 1 is greater than 3 is greater than 5. Okay, now apply next Newton's second law to either the student alone or the student box system explaining your ranking in a clear, coherent paragraph. Okay, so what we can say is that time T1 and T3 have the largest net force. Because of the smooth surface. The smooth surface that the box is on. So since there is not enough friction at this point, the net force is going to be larger. And then T5 is less net force, because of an increase in friction. Part 3, if A1 is 1.6 meters per second squared, calculate A3 and A5. Okay, so here's what's going on. At T3, the mass, the total mass, that's accelerating, doubles. Let's take a look at the picture so we can see this. At first, it's just the mass of the student accelerating. But then at T3, right here, you have the mass of the box and the mass of the student both accelerating. So the mass has doubled. Since mass is inversely related to acceleration, the acceleration in A3 is going to be half of A1. Okay, so the mass, the mass 3 is double. The mass at time 3 is double the mass at time 1, so the acceleration at time 3 is half the acceleration at time 1. So it would be half of 1.6 or 0.8 meters per second squared. Now at T5, the net force actually decreases at this point. Because remember, at T5, that's the lowest acceleration. So at T5, the net force has actually gone down. It's gone down from F F is the net force due to the friction on the student's feet. And if you go back to this right here, you have the friction in the student's feet that's, allowing the student to propel themselves forward. And at this time here, you not only have your net force is not just this, your net force right here is just F. Your net force for this example, for 5, is now causing force. Here's your causing force. And your opposing force, this little friction right here. Now that friction is, if you remember from the reading, experiences a frictional force. The box experiences a frictional force of 1/4 the student's friction. So this friction is actually 1/4 F. So the net force goes from F to 1/4 F, which means, goes from, let me back up, just calculate the net force. So causing force minus opposing force would be F minus 1/4 F equals 3/4 F. There we go. So the net force decreased from F to 3/4 F. Okay, so if the net force decreased, the acceleration decreased. So this means the acceleration in 5 is also 3/4 of the acceleration in 3, the time right before it, which is 3/4 of 0.8 meters per second squared, which means A5 would be 0.6 meters per second squared. This one, part 3 here, is a little tricky. So if you need to kind of pause and rewind to make a little more sense of this, please do so. Thank you.